Preparing. Right. Okay. Okay, so YouTube is now running, so we are online. I will start recording, and okay, so now we are on. Okay, welcome everyone. We have 17 participants so far, but people will join later, I hope. So today's speaker is Matt Nicholl from University of Birmingham. He did his master in Oxford, PhD in Belfast, which is the European Center for Supernovae, I can tell for sure. So he comes from the core of the supernova community and has been expanding this community in recent years. He's been a postdoc in Harvard, then moved back to the UK in Edinburgh, and now he's a lecturer in Birmingham. And Matt is specializing in superluminous supernovae. And I would like to thank Matt for very short notice joining for this seminar and giving us this opportunity to listen to your interesting stuff. Here's to you, Matt.
Yeah, thank you, Wukash. It's a pleasure to be here. Thanks for the invitation. So I usually like to start these things with a quick one-slide introduction to stellar evolution, because you need that to get to the supernova. So the star, any star, spends most of its life just fusing hydrogen into helium in the core. But stars more than about 8 times the mass of the sun can go on to fuse heavier and heavier elements until they eventually build up an iron core. And once the core of the star becomes made of iron, there's only so much it can support itself because nuclear fusion doesn't produce any more energy at that point. And when it becomes massive enough, it suddenly collapses. And when the core of the star collapses, it releases the gravitational binding energy. And this is enough energy to eject the outer layers of the star in a very powerful and very bright explosion that we call a supernova. So the image on the right is just an artist's impression of a supernova. And it's important to point out that these massive stars have very short lifetimes. So they only live for maybe 10 million years or so. So no life has had time to form on any of the planets in this picture. So no aliens were harmed in the making of this slide. So when these things do explode, they scatter this debris out into the interstellar medium. And these are super important because they disperse all of the elements that we need to form the next generation of stars and planets and life. And they leave behind these very beautiful supernova remnants. So this is the Crab Nebula and the remnant of Cassiopeia A, 2 nice nearby supernova remnants. But usually we only get a supernova nearby enough to see a nice remnant like this, if it's in our galaxy or a very nearby galaxy. So this happens once or twice per century. So most supernova studies are not looking at these nice resolved remnants, but rather looking at point sources in other nearby or even very distant galaxies. So we have 2 sort of main ways of looking at these supernovae in the optical. So it's to take images of these things or to take spectra to see what they're made of. So I'm going to quickly review sort of the main different types of supernovae and what the luminosity and the spectra of these things look like. So in any sort of fixed volume of space, the vast majority of supernovae that we see are what are called type II supernovae. So these are the explosions of red supergiants. So these are stars with massive hydrogen-rich extended envelopes. And so when these explode, the spectrum that we see is dominated by hydrogen lines. So you can see the spectrum on the right. You've got these very broad emission and absorption lines. They're all from hydrogen. This is the Balmer series you can see. And the light curve, the luminosity versus time for the type II supernova, has a very distinct behavior where for 100 days or so, the light curve is pretty flat. And this is because the explosion deposits all this energy into the hydrogen envelope, and gradually that envelope recombines and emits that energy. So that takes about 100 days. And afterwards, the light curve suddenly drops down onto this second part, which is a slope powered by radioactive decay of heavy elements made in the explosion. So supernovae make radioactive elements, especially 56 nickel, which decays then to 56 cobalt and ultimately to 56 iron. So we don't see the nickel here around the peak because it's all dominated by the recombination energy. But by 100 or 200 days, we can see a very characteristic slope as the cobalt decays into iron. So those are most supernovae in the universe, but not the only kind. So one very important thing that affects what we see is whether the star retained this hydrogen envelope until the point of explosion. So if the star loses its envelope, we get what's called a stripped envelope supernova, or a type 1b or type 1c supernova. And in this case, the spectrum looks quite different. So here we don't have the very obvious H alpha emission line here. It's at 6,500 angstroms. Instead, we have lines of intermediate mass elements, such as oxygen, calcium, and iron, and slightly higher velocities so that the lines look a little bit broader here. These lines are all broadened by Doppler shifts of the very fast expanding supernova ejecta. And if we go back to the luminosity on the left, you can see this time, at the peak of the light curve, we are directly seeing the power from nickel decaying into cobalt. And then the light curve settles on to roughly the same slope as the type 2 supernova as cobalt decays into iron. So those are significantly rarer than the type 2 supernovae. Probably come from slightly more massive stars that have lost their envelopes before explosion. Now, not all supernovae come from massive stars. The other kind of supernovae that we see a lot of are type 1a supernovae. And these are supernovae that actually come from white dwarfs. So in this case, the white dwarf, which is what's left behind from a low mass star at the end of its life, it manages to accrete some extra material, either from a nearby main sequence star or maybe another white dwarf collides with it. And when this gets above a certain critical mass, it's too heavy to support itself, it gets too hot, and you get a thermonuclear explosion that destroys the white dwarf. And in this case, actually, the light curve looks quite similar to the type 1bc supernova, because again, what we see is mostly radioactive energy from 56 nickel decaying to 56 cobalt, and then cobalt to iron. But this is a little bit brighter than the type 1bc supernova because it makes a larger amount of this radioactive nickel, up to half a solar mass of radioactive nickel. And by some magical standardization, you can use these to measure distances in the universe. They all have a similar peak luminosity. And so these are very important for cosmology. And this time the spectrum looks a little bit similar to the type 1b or 1c supernova, but we see slightly heavier species, a lot of silicon and sulfur. So those, for a long time, were the vast majority of known supernovae. For a century or so, most supernovae fell into one of these three classes. But this started to change in kind of the mid to late 2000s when we had essentially a new way of looking for supernovae. Previously, we searched nearby massive galaxies to try and find where regions of a lot of stars or a lot of star formation would be to look for supernovae. But eventually, we had the technology to look at the whole sky every couple of nights with blind, wide field surveys. And at this point, we started to see a much more diverse family of supernovae. And this included some really surprising events. So the ones I want to talk about today are called superluminous supernovae. So let me put this new class of supernova on the same plot as the others. So the superluminous supernova light curve stands out quite substantially from the other classes here. Not only is it quite a lot brighter, more than 10 times brighter than the type 1a supernova at its peak, but they also live for a lot longer. And when you integrate the luminosity over this light curve, these can emit thousands of times more energy than the traditional supernova classes. The spectrum of these events also looks completely different. So here we can see, first of all, the spectrum is much steeper with this really high slope up towards short wavelengths, which is telling us that it's very hot. If you approximate this as a black body. And this time the transitions of atomic species we see are quite weak. We see these shallow absorptions, mostly from ionized oxygen, oxygen 2. So these look totally unlike on any of the traditional supernova classes and were totally unexpected when they came along 10 years or so ago. So yes, before I talk any more about these, I should do a quick bit of bookkeeping, which is that not all of the most luminous supernovae show this oxygen-rich spectrum. The ones that do, and the ones that I'm talking about today, are called type 1 superluminous supernovae. But there is also a class of type 2 superluminous supernovae that show strong and narrow hydrogen lines in the spectrum. And these can be just as bright or even brighter at times, but we think we understand a little bit more where the luminosity comes from in those. So today I want to focus on the really mysterious class of type 1 superluminous supernovae. So why are these things so important? So the fact that these were not predicted before the discovery shows that we really lack something fundamental in our understanding of stellar evolution to tell us how stars are supposed to end their lives. The fact that these are so rare also indicates they might come from extremely massive stars. So these superluminous supernovae only make up about 1 in 10,000 supernova explosions. So if these do come from the most massive stars, that can tell us something about stellar evolution in a regime that's very hard to probe otherwise, because these massive stars are so unusual. And because they're so bright, we can see them over very vast distances. So we can see them in the very far off universe and potentially use them to measure distances at much greater redshifts than we can do for type 1a supernovae. So we could measure the expansion of the universe over a larger distance. And perhaps if we can see them far enough away with some upcoming telescopes like James Webb Space Telescope, we might be able to even see the explosions of some of the first stars to form in the universe. So there's all kinds of cool stuff we can do with superluminous supernovae. But first, we want to understand what actually is going on here. What is the dominant luminosity source that causes these explosions to become so bright? So that's kind of the main question that I want to talk about today. So the first clue for the weirdness of superluminous supernovae, and partially the reason why we didn't find them for such a long time, even though they're so bright, is because of whereabouts they actually explode. So I mentioned before that historically supernovae were generally found by looking at big, bright, nearby galaxies. And superluminous supernovae were only found when we started to do untargeted searches that take into account all different kinds of galaxies. So if we start with the images on the left here, the top panel shows just an image from the Pan-STARRS survey of a superluminous supernova called 2015 BN. And below that is an image of the same patch of sky from the same telescope before the explosion occurred. And what you see is that the supernova did not occur in this sort of big bright galaxy at the left. It occurred in this tiny little faint smudge of a galaxy in the center. And this is kind of the theme of superluminous supernovae, that they really do prefer to occur in very low mass and faint galaxies. So to make this a little bit more quantitative, if we look at the plot on the right, this plot shows the stellar mass in various galaxies on the x-axis compared to the metal content, which we parameterize here as the ratio of oxygen to hydrogen on the y-axis. And so the blue points here are type 1 superluminous supernovae. And you can see these points tend to cluster down towards the bottom left-hand corner of the plot. Now, if we compare these to the gray points are a volume-limited sample, so an unbiased sample of just general background galaxies. And these points are sized in proportion to the amount of star formation that's occurring in those galaxies. So a larger gray point means that more stars are being formed there. So if superluminous supernovae were simply to occur from very massive stars with no other factors at play, you would expect that most of them would occur where a lot of star formation is happening in order to produce these small number of massive and rare stars. But that's not what we see at all. The vast majority of star formation is happening in the top right of the plot, where the big gray circles are, whereas the superluminous supernovae are happening in these low mass galaxies with very, very little star formation. So this suggests we need an extra ingredient in stellar evolution to make these unusual systems. So it's been proposed that this metal content is one of the key factors in making these strange explosions. So this plot shows what we call the efficiency. So basically just the number of superluminous supernovae per unit star formation as a function of the metallicity of the galaxies where they occur, or equivalently the mass on the bottom x-axis, the mass of that galaxy. So what we see is that at a particular metal content, which happens to be roughly half the metal content of our galaxy, the production efficiency for superluminous supernovae, plotted in blue, dramatically drops. It really plummets. So that suggests that superluminous supernovae are very, very difficult to make above a certain metal content for the stars in that galaxy. Now, interestingly, we see a very similar behavior with a totally different kind of explosion, or potentially a different kind of explosion, which is long gamma ray bursts. So gamma ray bursts are highly jetted, high energy events that have been discovered in the distant universe that also are linked to the deaths of massive stars, but have been around for a lot longer than superluminous supernovae. And in this case, the purple curve shows that also for GRBs, the production efficiency suddenly drops above a particular metallicity. A little bit higher in this case, this metallicity is around the same metal content as our galaxy. But this was the first clue that there might be some kind of link between superluminous supernovae and these other very, very powerful explosions in the form of GRBs. Okay, so yes, so I think this superluminous supernova and GRB connection is pretty actually fundamental and goes a little bit beyond just the host galaxies. So the next clue that these two classes of explosion were related came from the spectroscopy. So on the left here, you see the same plot from earlier to show superluminous supernova spectrum at peak, this very hot, steep, sloping blue spectrum. Well, I say blue as in it's hot. The color on the plot here is orange. But the plot on the right shows a superluminous supernova not at its maximum brightness, but rather a month or so afterwards. So this is the spectrum in pink. And here we compare this to a number of spectra from type 1c, so stripped envelope supernovae, and particularly GRB supernovae. So the GRBs we've seen to date have been associated with what's called a broadline type 1c supernova. So this is a hydrogen per supernova with very high velocities. So these Doppler shifts broaden out all of the absorption and emission lines in the spectrum. So that gives you something that looks like the bottom spectrum. So supernova in 1998 BW was the first GRB supernova. And you can see that about a month after peak, the superluminous supernova spectrum actually now has these broad lines and this much less steep continuum shape. And at this point, it looks quite similar in many ways to what we see in these broadline type 1c or GRB associated supernovae. So there's two important clues to take away from this. One is that there is some kind of connection between superluminous supernovae and gamma ray bursts. And the other connection, or the other takeaway rather, is that part of the reason superluminous supernovae look so different from other supernovae may simply be a function of how hot they are. So I like to think of superluminous supernovae as actually being super hot supernovae. So once they cool down, then they start to look a little bit more like normal supernovae. But for some reason, they're much, much hotter at the peaks of their light curves than any other type of supernova. So what could be making this extra heat to give us this incredibly high luminosity in these events? So I list here some possible mechanisms that have been discussed quite extensively in the literature. So the first one, and perhaps the most obvious one, is to produce a large mass of 56 nickel. So this is the main power source in most kind of traditional supernovae. And type 1a supernova produces up to sort of half a solar mass of nickel. These superluminous supernovae are a few tens of times brighter than that. So perhaps you just produce, around 10 solar masses of nickel and you can get this luminosity. So there are some ways to achieve that, which I'll talk about shortly. But you do need a very, very massive star. The second mechanism that's been discussed at length is what's called circumstellar interaction. So in this case, the supernova ejecta are expanding with a large kinetic energy just coming from the supernova explosion. But the supernova is surrounded by some dense medium, probably some gas that had been expelled from the star prior to the time of explosion. Now, when the supernova ejecta that are moving very rapidly collide with this slow-moving material, all of that expansion energy is converted into thermal energy, and this then gets radiated away. And this can lead to very high luminosity too if you have a circumstellar mass that's comparable to the ejected mass in the explosion. And in fact, this is what we think is happening in the type 2 superluminous supernovae, where we see these narrow hydrogen emission lines. The final mechanism here is what's called a central engine. So in this case, you've got something that's basically rotationally powered. So this could be if a very rapidly rotating star collapses to a rapidly rotating black hole or neutron star, and you can extract that rotational energy, you might be able to put in a large amount of energy to keep the supernova hot as it expands. This might function somewhat similar to a gamma ray burst, but occurring over a much longer period of time. And I always like to leave open the possibility that all of these are completely wrong, and we need to think of a new mechanism to explain superluminous supernovae. But these are kind of the big three that are debated in the literature at the minute. So let's look at the first one of these, the simplest one, the question of, do superluminous supernovae just make more 56 nickel than a regular supernova? So yes, as I mentioned, you probably need several tens of solar masses of nickel to match these peak luminosities. But there is a model that's been around for a very long time that can do this, and this is what's called a pair instability supernova. So the prediction here is that in stars more massive than sort of 100 times the mass of the sun, or the helium core is more than 65 times the mass of the sun, the temperature in the core gets so high that photons become unstable and are converted to pairs of electrons and positrons. When this happens, the core suddenly becomes very unstable, it loses its radiation pressure and contracts, and it gets hotter and hotter and hotter in a runaway process that eventually leads to a complete thermonuclear detonation of the star. So you suddenly blow up a star of 100 times the mass of the sun, you can make an awful lot of radioactive nickel. And in fact, one of the earliest superluminous supernovae, supernova 2007 Bi, which is the red points in this plot, famously looked quite a lot like some of the predictions of what this pair instability supernova model might look like. So the colored lines here show some predictions from simulations, and you can see that that's a pretty reasonable match. So at that point in the sort of late 2000s, it looked like the nickel model might well be the explanation for the high luminosities in superluminous supernovae. But this changed then a few years later when we started to discover these events much sooner after the time of explosion. So the plot now on the left shows in red the same supernova, 2007 Bi, and two events discovered by the Pan-STAR survey very soon after the time of explosion. So you can see that PTF 12 DAM here, the supernova plotted in black, it's caught way before the peak, and you can see the light curve brighten up to its maximum in a period of around 50 days. This looks very different suddenly compared to the pair instability models. So the colored curves are the same models as before. And you can see these all take at least 100 days, or sometimes much longer, to reach the peaks of their light curves. And the reason for this is quite simple and therefore very difficult to avoid. And that is simply that there is so much mass in these explosions. So the time taken for supernova to reach its peak brightness is set primarily by the time it takes photons to diffuse through the expanding ejecta. And the time that takes is proportional to the square root of the ejected mass. And so for these 100 solar mass explosions, it turns out that it takes around 100 days for the photons to escape. And that's quite hard to square with the observations of superluminous supernovae. And in fact, as more events have been discovered, it turns out the sample is incredibly diverse, and many events actually evolve even faster than the ones I just showed. And so it's very hard to explain how these rapidly rising and fading superluminous supernovae could ever be explained with this very, very massive pair instability model. But there is one or two objects. You can see the blue points here show a very, very broad light curve. So occasionally there's a superluminous supernova that may be consistent with a pair instability explosion, but it seems like at least the vast majority of these things are not. So that model's kind of become a little bit less popular in the last few years. So one of the best ways to actually work out what the power source is in these things is to wait for a long time. So a lot of models can sort of roughly get the right answer around the peak of the brightness. But at this stage, as I said, the photons are diffusing slowly through the ejecta. So it's very hard to see deep into this material. But over time, the supernova expands, the density decreases as it does so, the temperature goes down, ionized species start to recombine, and eventually this whole debris becomes optically thin. And at that point, we're in what's called the nebular phase, and you can see all the way into the interior of the explosion. So at that point, the innermost regions stop being a black box, and we can see the composition and what kind of nucleosynthesis occurred deep in the core. We can diagnose the structure of this ejecta and learn about the asymmetry, and we can derive clues about the power sources and progenitors. So now I want to talk about a study of relatively large sample of 12 superluminous supernovae and about 40 spectra, all obtained during this so-called nebular phase that allows us to probe the innermost regions of the ejecta and try to learn something about what really powers these explosions. So this is just a quick snapshot of the data. So you can see all these different superluminous supernovae observed at times from around 100 to 500 days after the explosion. So let me just go through some properties now of this sample. So starting with the average spectrum, the top plot here shows the average of all of these data, and the bottom plot shows an average again, but this time the red curve shows the average of the left-hand column. If I just go back a slide. So this is at sort of relatively early times, around 1 to 200 days after the explosion. And the blue points, the blue curve here shows the spectrum at later times, so the average at sort of 300 or 400 days after the explosion. And you can see that the two averages look quite similar for the most part, except for one spectral line. So this oxygen 1 6300 angstrom line only appears very late in the evolution, whereas the other nebular lines appear significantly earlier. And what's very puzzling here is that the calcium 2 line right next to it at 7300 angstroms, it has the same critical density as oxygen 1, as in this line should only become strong at the same density where oxygen 1 becomes strong. And yet the calcium 2 line appears much earlier than the oxygen 1 line. So there's something very puzzling going on here if these lines are forming only because the density is decreasing as the ejecta expand. So that's something we'll come back to in just a moment. The second point I want to make here is if we compare this spectrum to normal stripped envelope supernovae in the top here. So the average normal supernova 1c is plotted in blue at a similar time after explosion. And you can see that they are quite similar here. There seems to be a lot of similarities in which elements are made and which lines are strong in normal type 1c supernovae compared to superluminous supernovae. But the big difference is in the blue part of the spectrum, kind of below 5,000, 6,000 angstroms, where superluminous supernovae are much, much brighter than normal type 1c supernovae. And this region of the spectrum is dominated really by emission from iron 2. And what this means is that superluminous supernovae seem to produce a significantly larger mass of iron than normal type 1c supernovae. And this is often interpreted as a diagnostic of the mass of the star. A more massive core can produce more heavy elements. So it looks like superluminous supernovae come from more massive stars than normal type 1c supernovae. So if we look at the bottom plot, we can see the comparison to GRB supernovae. In this case, we again see the same spectral lines, but this time the flux match in the blue part is much, much better. So it looks like superluminous supernovae probably produce a similar amount of iron as do GRB supernovae, and so may come from similarly massive stars to gamma ray bursts. The other interesting thing here is that superluminous supernovae show this really strong and narrow line from oxygen 1 at 77, 74 angstroms. And this is a recombination line. And this line is not strong in either the normal type 1c supernovae or the GRB supernovae. So this is another important clue about what's happening in the core of superluminous supernovae that we're going to circle back to when we try to interpret all of this. So the next thing that we looked at, as well as the average spectrum, was to measure the velocities of all of these key lines. And we can make a simple assumption here that the ejecta expand in what's called homologous expansion. And this just means that the outermost material is traveling faster than the innermost material. And this is what happens if you inject a shock centrally into sort of a spherical star and let it expand that way. So this is pretty common in supernovae. So what we see in the plot here is just the velocity of each line measured from its Doppler width as a function of time. And so the oxygen 1 6300 line starts off emitted far on the outside of the fastest moving material, but gradually over time we see this emission from slower and slower moving stuff, which means we're seeing it from deeper and deeper inside the debris. In contrast, the other oxygen line, the 77, 74 line, is always at a much lower velocity coordinate. So we're always seeing that line being emitted from deep inside the supernova ejecta. And the calcium line, the one that's unusually strong compared to the oxygen 1 line, also seems to be emitted from deep interior of the star, similar to this oxygen recombination line. So by knowing where in the ejected different lines come from, we can try to piece together where the energy is being injected, which we'll do shortly. The next clue in this story is the ratio between some of the spectral lines. So the ratio of the calcium-2 7300 line to the oxygen-1 6300 line is often used as a diagnostic of the exploding core mass. So here, the points are just the measurements for each spectrum plotted as a function of time. And the sort of shaded regions show some models predicting what this line ratio should be for different masses of the exploding stellar core. And you can see that most of these measurements cluster down towards the bottom of the plot, which is only really achievable for core masses of around 6 solar masses or greater, which indicates these probably come from significantly more massive stars than most supernovae, which have cores of maybe 3 solar masses or so. But a few of these events are kind of anomalous. So you can see a few points here that sit way above any of these theoretical predictions. And in this case, what we think is happening is that the strong line at 7300 angstroms is probably not calcium-2, but rather oxygen becomes ionized, and we see oxygen-2 instead of oxygen-1, because the oxygen-2 has a strong line at around the same wavelength as calcium-2 at 7320 angstroms. So for some reason, a small number of superluminous supernovae show very strong ionization of oxygen, even at very late times when the ejecta should have cooled down a little bit. The other important line ratio is between 2 different calcium lines, and this ratio is a diagnostic of the density, the electron density in the emitting region. So for the ratios that we measure between the 7300 line and the near-infrared triplet, we consistently measure a ratio of greater than 0.5 between these 2 lines, and that needs an electron density in the line-forming region of around 10 to the 8 electrons per centimeter cubed. Now, if we took a simple kind of model where we've got a 6 solar mass core, as we think we see from the other line ratio, and we expand that at the observed velocity of around 7,000 kilometers per second until a time of 300 days, like we see here, the electron density that you would predict is around 10 to the 7 per centimeter cubed. So that's about an order of magnitude less than what we measure from the line ratio. There's a simple way to increase this density without increasing the ionization, and that is to make the ejecta clumpy. So instead of having a sort of uniformly filled volume with this ejecta, instead you have a fairly sparse medium interspersed with dense clumps. So the density in the clumps is an order of magnitude higher than the density of the medium in between, but most of the emission comes from these clumps rather than from the interclump medium. So this line ratio suggests that superluminous supernova ejecta is quite highly clumped. And the final line to look at here is this strong oxygen recombination line I mentioned, because we can use that luminosity as a function of time as a double check on this clumping. And we can do this check because we saw that this line comes from the same part of the ejecta, the low velocity innermost regions, as does the calcium emission. So this plot shows the luminosity of that recombination line as a function of time for all of our sample. And overplotted here is the theoretical luminosity for the measured electron density of 10 to the 8 per centimeters cubed and different filling factors where the clumping is given by 1 over the filling factor. So a lower number for the filling factor means the ejecta are clumpier. And it turns out that indeed all of the objects lie below where we would expect for a fully sort of homogeneously populated sphere. So all of these events require clumping to push the luminosity in this line down to the region where we see. So that was a lot of information that I just threw at you. So I'll just quickly summarize each of these key observations before we try and piece this together so we can learn what it actually tells us about the geometry and the power source of the explosion. So first of all, we saw that the superluminous supernovae have a fairly massive progenitor as diagnosed from the iron and the ratio of oxygen to calcium. We learned that the calcium-2 emission seems to appear surprisingly early compared to what you would expect for the critical density of calcium and oxygen being the same. We saw a strong oxygen-1 recombination line that comes from very low velocity coordinates, so a lot of recombination occurring deep inside the ejecta. And we saw the luminosities of these low velocity lines in the interior all seem to indicate significant clumping of the material. And finally, we saw that a very small number, but definitely some superluminous supernovae show an unusually high ratio of oxygen 2, so ionized oxygen, compared to neutral oxygen 1, which you don't usually see at supernovae so late after the explosion. So now I want to kind of convert this into a simple model. So I think there's a consistent explanation for all of this. So let's start with the ejecta structure for normal type 1c supernova. So when the supernova explodes and the shock wave goes through the star, this causes nucleosynthesis of heavier elements, and you end up with a distribution that looks something like this, where towards the center you've got heavier things, and towards the outside you've got slightly lighter things. So this is a pretty standard setup here, where you've got iron in the center, then you've got silicon and sulfur, and as you go towards the outside, you get more more oxygen and intermediate things like that. And calcium tends to be towards the center of this distribution of elements. And now what we do is to insert some kind of very strong power source right in the center of this explosion. So a central engine of some sort that's inputting energy right in the middle of the debris. So putting all this energy in the center causes an overpressure, and this drives kind of a bubble that hollows out a cavity inside this material. And as you kind of put all this pressure in the center, this causes really Taylor instabilities and turnover, and that leads to clumping. So the ejecta start to clump from the inside out. Now, in between these clumps, the density is very low, and this means that you can get kind of the nebular appearance. So this low density material that emits these various emission lines before the outside of the ejecta. And this might explain why we see the calcium 2 appear before the oxygen 1, even though these should have similar critical densities. So the density becomes low on the inside before the density becomes low on the outside, where most of the oxygen is. So that can explain that kind of anomaly. Then, because you've got all this energy input into the center, this is absorbed and causes oxygen to ionize and recombine. And this is how you get the recombination lines coming from the center of the debris. So this narrow oxygen 1 recombination line that we saw. And finally, some recent simulations with the code Cloudy show that if you have a central engine in a supernova, ionization fronts, so the region out to which the ejecta are ionized, does not recede deeper into the ejecta even as this material expands. So what that means is if you manage to ionize the oxygen early, the oxygen can stay ionized no matter how much the nebula expands. And this explains how you can have persistent oxygen 2 emission even at very late times in superluminous supernovae. And so that's kind of the artist's impression model, but there are some real simulations that reproduce this behavior. So here's a recent simulation from Suzuki and Maeda. And the density shading here shows this sort of really Taylor instabilities and turnover that generates the clumps. And we even have some theoretical spectra produced for different layers in this colorful picture I showed. This is from the carbon burning zone, where most of the oxygen emission comes from. And for different masses of ejecta, you can change the ratio of oxygen 1 to oxygen 2 and produce these this kind of variation that we've seen. So I think that by putting a central engine in the center of this sort of normal-ish type 1c supernova debris, you can reproduce many of the main features that we see in the late-time spectra of superluminous supernovae. So if you believe me that you need a central engine in the center of this material to reproduce the observed properties, the next question is what actually the central engine might be. So the core of the star collapses either to a neutron star or a black hole, and either of these can have significant rotational energy that we might be able to tap into. In GRBs, for example, a popular model is that it's accretion onto a rapidly rotating black hole that powers the jet to give you a gamma ray burst. But those GRBs only last for a few seconds, whereas superluminous supernovae stay bright for weeks or even months. To power a superluminous supernova with accretion onto a black hole for such a long time, you can need to accrete up to 1,000 solar masses, according to some estimates. So I don't think that these are 1,000 solar mass stars that are exploding, and therefore I think that the black hole explanation is quite unlikely. So that leaves the alternative, which is a neutron star. But more specifically, what we mean here is what's called a magnetar, so a magnetized neutron star. Because if you have a magnetic field, you're able to tap into this rotational energy. But so magnetars are known in our galaxy. There are plenty of examples of neutron stars with high magnetic fields, up to 10 to the 15 Gauss. It's a very strong magnetic field. But all of the ones we know locally are slow rotators. However, if they're born with a high rotational energy, this can really significantly influence what happens in the explosion. So if your spin and magnetic axes are misaligned, as this rotates, it emits as a magnetic dipole. That's quite an old idea. But it turns out you can model this really simply. So the luminosity that you extract from this rotating magnetar, you have a power that scales as the magnetic field squared over the spin period to the fourth power. And that lasts for a time scale that goes roughly as the spin period squared over the B field squared. So you end up with a theoretical light curve that looks something like the bottom right here. And so by constructing a simple model with this, you can fit this to the observed light curves of superluminous supernovae, and you can actually measure what spin period and magnetic field you would need to reproduce the observed population of superluminous supernovae. So that's what I want to look at now. We're going to model the light curve and find out what kind of magnetar you would need to power these superluminous supernovae. And hopefully that will tell us something about what kind of stars you would need to make those magnetars. So for this model, we're going to take a fairly simple analytic model because we're exploring a large parameter space and fitting to a lot of data, and it's too expensive to run full hydrodynamic simulations. We're going to use all the available information. We're going to take the observed photometry in UV, optical, and infrared to maintain all the temperature information that gives us. And we're going to use MCMC, Markov chain Monte Carlo sampling, to try and get realistic error bars and marginalize over some nuisance parameters that must be included in the model. So the free parameters of the model are listed here. So the main things we're interested in are the spin period of magnetar, its magnetic field, and of the supernova itself, how much mass was ejected and at what velocity. And finally, how efficiently does the spin down energy from the magnetar couple to the supernova ejecta to heat it up. The parameters that we don't really know what to do with and we need to marginalize over are the opacity of the supernova ejecta, how fast photons can move through it, the mass of the neutron star, and the angle of spin and the extinction in the host galaxy. But we'll include all of these in our models. So I'll just jump straight to some results. Here are examples of observed superluminous supernova light curves overlaid with their best fitting models from these magnetar simulations. And you can see that for a whole range of different photometric bands from UV, optical, infrared, with very different sampling, and supernovae at very different redshifts, from nearby ones at redshift around 0.1 to quite distant ones at redshift greater than 1. In all cases, we get a pretty good fit of model to data. So we're fairly confident that we've extracted these magnetar parameters as best we can. So this is the corner plot showing the best fitting parameters and the correlations between them, summed over all of our sample of about 40 or so superluminous supernovae, which is all the ones available at the time when we did this study. But the sort of panels of interest here are highlighted here. I've made them big so you can see them. The spin versus the B field. So you can see that we've constrained this just to this little wedge in the parameter space. So it's actually quite tightly measured by our sample. And also the ejected mass versus the kinetic energy of the explosion, which those things seem to be slightly proportional to each other, but again, are very well constrained by the model. So now I'd like to try and use these to see what we can pull out about the fundamental processes needed to make a superluminous supernova. So what these plots show are the same as the previous two plots, except that this time, instead of sort of a shading, I'm showing every individual event with its error bars. So on the left, we have the spin period versus the B field again. And overlaid on this are some theoretical curves for where the spin down time scale of the magnetar, this p squared over b squared, is equal to the diffusion time of photons through the ejecta. So this was the sort of square root of mass that we mentioned earlier. So the dotted and dashed curves show where these two timescales are mismatched by a factor of 10. And what we see is that nearly all of the superluminous supernovae kind of cluster in between these two lines in the region where the magnetic spin-down timescale is comparable to the photon diffusion timescale. Now, the only exceptions to that rule are in the top left. So events with very short spin period that have essentially a very large rotational energy that's available to tap can still become bright even if their timescales are a bit mismatched. But otherwise, at longer timescales, you really need to match these two timescales to make the explosion bright. So this is how you maximize the luminosity that comes out of these explosions. The plot on the right shows the spin period versus the ejected mass. The black lines have the same meaning as before. And the red lines here show where the photon diffusion timescale is equal to 30 days, 100 days, or 300 days. And you can see the superluminous supernovae live in the region where the diffusion timescale is of order a few tens of days. So this is the time it takes for the light curve to peak, which we've seen before it takes a few weeks or months. And so you put these two things together, what we see is that you can maximize the luminosity by matching these two timescales. And the maximum luminosity is in this superluminous regime far above other supernovae when this happens on a timescale of a few tens of days. So those are kind of the only two ingredients you need with this magnetar to get a superluminous supernova explosion. Now this model makes a prediction, which is that if you have a central engine inside a stripped envelope supernova, similar to a type 1c supernova, or even similar to a GRB supernova, by changing some of these engine parameters, by making the spin down period slower and slower and slower, you should gradually reduce the luminosity to a point where the engine basically becomes invisible. So if this were true, we would expect there to be a fairly continuous distribution of peak brightness between stripped envelope supernovae with an engine and those with a very weak engine. And so the luminosity of superluminous supernovae should be continuous with GRB supernovae and then with normal type 1c supernovae. And indeed, just in the last couple of years, as these samples have finally become large enough, this is exactly what we see. So the plot here from Annalisa Dacia shows the peak magnitude distribution, especially in the bottom panel where this is corrected for the distance over which we can see brighter and brighter events. We see a very continuous distribution of brightness from a normal type 1c through GRB supernovae up to superluminous supernovae. So this can be achieved simply by dialing up this strength of this engine in terms of the B field and the spin period. The other prediction this model should make is the rate of superluminous supernovae. So we saw that these account for about 1 in 10,000 supernova explosions. So the parameters of the model can be used to estimate whether that rate seems realistic or if we've done something wrong here. So let's do a quick sanity check. If we start with the ejected mass, so we saw that superluminous supernovae have ejected masses in the range of sort of 4 to 40 solar masses. That corresponds to 0 age main sequence masses, so the mass the star was actually born with, including the hydrogen envelope, of greater than about 20 solar masses. And that is about 25% of all the stars that should make supernovae. We also saw that the spin period had to be a few milliseconds, and that corresponds to an angular momentum in the core of the star, assuming this core of the star is able to collapse to this millisecond magnetar of around 10 to the 15 centimeters squared per second. And this is the angular momentum that we see in about the top 10% of massive stars known in the local universe. We measured the magnetic field of these things should be greater than 10 to the 13 Gauss, and this is about the top 10% of all known neutron stars, so the magnetars we see in our own galaxy. And going way back to the start of the talk, we also saw that nearly all superluminous supernovae occur at metallicity less than about half the metal content of our solar system. And about 20% of star formation in the local universe happens at these low metallicities. So if we make the most naive possible assumption that all of these parameters are independent of each other, we can estimate the rate of superluminous supernovae as a fraction of all supernovae by just multiplying these four numbers together. And if you do that, you work out that superluminous supernovae should correspond to about 5 times 10 to the minus 4, or a few in every 10,000 supernovae in the universe. And that's pretty much exactly what we measure from current surveys. So although this is a very, very simplistic calculation, it does at least show that the model here where the central engine powers the explosion accounts not just for the sort of main light curve properties and the late time spectra, but also for the low rate of superluminous supernovae. So this is where I have to add my caveat, which is that, although the central engine seems to do a very good job of explaining these things, these massive stars have lost their hydrogen envelopes, and so there should be some circumstellar material ejected before the explosion. So whereabouts is it? It's got to be there somewhere. So in fact, some superluminous supernovae do show evidence of interacting with some dense medium around the star. So this was kind of the competing power source in terms of the circumstellar interaction. So superluminous supernovae show interaction signatures, both in the light curves, where we sometimes have these bumpy structures that suggest the supernova is banged into something, and also in the spectra, where sometimes you suddenly see the appearance of a strong hydrogen line in a previously hydrogen-poor supernova, which means it must have caught up to some hydrogen-rich material at some distance from the star and suddenly collided and excited that hydrogen emission. So there is some circumstellar interaction, but this usually seems to be at very early times or very late times and may not be affecting too much the peak of the light curve. So I think we can still believe our model fits. But this hasn't stopped others from arguing that circumstellar interaction might actually still be the dominant power source in these events. So what we really need is a direct test that can distinguish in a direct comparative way between these different models for the luminosity, if you really want to believe my story about the magnetars. So there's at least one direct test that's been proposed that can do this. And this is the slope of the light curve at very late times. So around the peak of a supernova light curve, the shape is set by diffusion processes as the photons escape from the expanding ejecta. But eventually, when this becomes optically thin, similar to what we saw in the nebular spectra, the slope should track the power source that's actually heating up the explosion. So if it's a radioactively powered explosion, like a normal type 1A supernova, for example, the slope at late times is just the slope of the dominant radioactive half-life. So that's why all the supernovae look the same when they were cobalt decaying into iron. If you have a circumstellar interaction, the dominant process is diffusion of photons. So this is also an exponential shape decay, though in this case, the slope is not any particular radioactive nucleus. So it can be an exponential with any slope you want, depending on the density profile. But for the magnetar, we don't predict an exponential, but rather we predict a power law. So this is the time to the -2 that you get from magnetic dipole spin down. So if you can track a superluminous supernova for long enough, if it's a magnetar, the light curve will flatten. If it's something else, the light curve should keep declining exponentially. The problem is that this is very hard to observe because superluminous supernovae are generally very far away. Because these things are so rare, we only tend to discover them when we probe a large volume of space. So it's only been in the last couple of years that we've had superluminous supernovae nearby enough that we were able to observe them for long enough as they faded to track into this regime where we can see the difference between these curves. So I want to show the first example of this now, and this is from supernova 2015 BN, which you saw right back at the start of the talk. So I can remind you, here's a picture of it at peak and a picture of its very faint host galaxy. And the big panel here is the SIDS between 2 years and 3 years. So we're very confident that this little point source is, in fact, our aging supernova. So we were able to subtract off a model for the host galaxy and leave behind just the supernova light and measure the brightness of this thing. So let's see how we do in our test of these different models for the luminosity. So first of all, this is the light curve before our Hubble observations. So this is up to sort of 400 days after the explosion. And at this point, it's very hard to distinguish. You could fit this with a wide range of models. It's even kind of similar to the decay of 56 cobalt. But if we add our Hubble observations, we see something very different. Here, after around 500 days, the supernova has become much fainter than its host galaxy, but we see the light curve is now significantly flatter. And in particular, it's much, much flatter than the decay of radioactive cobalt. So this is another kind of, I think, the final nail in the coffin for a model where you're trying to power this with a large mass of radioactive nickel. This can't explain why the light curve would flatten like this. And in fact, this flattening really strikingly seems to track a long-standing prediction of this magnetar spin-down model. So the original prediction was that this would go as luminosity as time to the -2. But if you account for the fact that the density is decreasing, as some later authors did, and so less of this energy gets trapped and changed into optical light, it predicts a steeper slope closer to t to the -4. And so when I fit this data with a Power law model, in fact, the best fit Power law is luminosity goes as time to the -3.8 to 3.9. So very, very close to this, the magnetar in the sort of maximally steep regime where the ejected density is becoming low. So I think that this is a really, really nice piece of evidence that we really are seeing a magnetar in at least this superluminous supernova here. We can fit this again with our same model we used before. This is the magnetar model fit to the full UV to infrared data, and including our very late points in the optical bands. And in fact, we get pretty much exactly the same best fit parameters as we got before, which suggests that we actually could have predicted this flattening if we really thought about it and known exactly when to observe. But it's nice to see that this observations pretty nicely track our predictions. Because we're able to observe this for so late, we're also able to better constrain the efficiency of how well this energy is converted into light in the supernova ejecta. So this is this kappa parameter, which this 0.01 centimeters squared per gram will be quite important in just a moment. Generally, this is very hard to constrain because it only really becomes an important parameter well after the peak of the light curve. So yes, apart from the fact that this confirms that superluminous supernovae can flatten at late times, there's also another important implication here, which is what's been termed the missing energy problem. So this plot shows the same light curve as before, up to the 2 years after the explosion. And the dashed dotted line that goes through the points here shows the best fit magnetar model, including this low trapping efficiency, this kappa 0.01. The purple curve then shows the same parameters, the same ejected mass, the same magnetar spin period, etc., in the case of fully efficient trapping. So no energy is leaking out, it's all being converted into optical light. And so you can see the purple curve gives you the same answer at the peak of the light curve, but then it declines much slower. This is the t to the -2 versus t to the -4. And so this purple curve is more representative of the total energy that's available. And the blue curve is the total energy that we actually see. So there must be some missing energy that's the difference between these two curves. And that's plotted in red. So the energy can't just disappear, it has to go somewhere. So the big question then is, where does this missing energy actually escape from the supernova? Does it come out in particles or in some wavelength that we're not observing, or where does it go? So we know it's not in the X-rays, because this plot also shows some deep X-ray limits in black, these down pointing arrows that suggest less than 1% of this missing energy can be in the X-ray band. We got some similar observations in the radio, and we see that it's not there. But this kappa parameter gives us a clue. So this trapping opacity of 0.01 centimeters squared per gram is actually almost the exact theoretical opacity for pair production in GeV to TeV photons inside some expanding nebula. So this suggests that maybe the photons from the magnetar are escaping at GeV to TeV kind of gamma ray energies. So it's very hard to observe these in the gamma rays unless they're very nearby. So this is a tough experiment to do. But I think the final smoking gun we need to confirm this picture is to find these gamma rays. And so we're running a new project now with Veritas Gamma Ray Observatory, and basically waiting for the next superluminous supernova that's close enough to us to be able to detect the amount of missing energy we inferred from those previous observations. So hopefully over the next few years, we'll get lucky, we'll get a really nearby superluminous supernova, and we might be able to see some gamma rays directly and confirm the picture that I've presented today. And our hopes for this are pretty high because we have new surveys coming along that should greatly increase the discovery rate of superluminous supernovae. In particular, I'm thinking of the Rubin Observatory with the large synoptic survey of space and time. And this LSST will increase the rate of discovery of superluminous supernovae by at least 1 or 2 orders of magnitude. So this plot shows some predictions Assi Villar did recently. And I've added on the current rate of superluminous supernova discovery, which is a few tens per year at low redshift from surveys like ZTF, ATLAS, PanSTARRS, OGLE, and then LSST from both the targeted deep drilling fields will discover probably hundreds of superluminous supernovae per year. And the main wide fast deep survey will discover probably thousands of superluminous supernovae per year. So at that point, the challenge will not be to get superluminous supernovae. It'll be to identify them early, make sure we get good spectra, and get enough data we can really model these things in detail. And so I think that takes me to the conclusions. So I've shown a picture here where new statistical samples are starting to finally reveal what I think is the power source in the most luminous supernovae. And most evidence seems to point to a magnetar central engine, so the spin down of a newly formed neutron star with a strong magnetic field. There might be some circumstellar interaction on short time scales, but most of the diversity comes from the ejected mass and differences in the engine parameters. They seem to come from very massive stars and probably are quite closely linked to the progenitors of gamma ray bursts. And the connection here is probably that both require very rapid rotation. And finally, I'm looking forward to the next few years when LSST will discover thousands of these events, and we can do even more detailed modeling of a much larger sample to hopefully determine what stars are really exploding here to make superluminous supernovae. So with that, I'll thank you very much for listening, and I'm very happy to take some questions.
Okay, thank you, Matt. I'll do the clapping here.
Thank you.
Are there any questions from the observatory staff, people on Zoom? Please unmute yourself and maybe show your face if you want to ask a question.
So this is Tomek. May I ask a question?
Sure, go ahead.
Okay, so I understand that you require a magnetar to explain the superluminous supernova. Now, is it the other way? Do you require that every magnetar is born with a superluminous supernova or not?
I don't think that that's required, and unfortunately, it's quite difficult to constrain. So the magnetars that we know about mostly appear to be fairly slow rotators, but we don't know the rotation period when they were born. So to get a superluminous supernova, it needs to be born both with the high B field and the rapid rotation. So if there is a wide distribution in the spin periods at birth, then we expect that probably many magnetars will be formed without a superluminous supernova. Whereas if they're all born rapidly rotating, then likely most magnetar births would result in a superluminous supernova. But I think it's more likely to be the former. So I think the observed numbers of galactic magnetars compared to the observed rates of superluminous supernovae suggest that probably lots of magnetars are born without making superluminous supernovae.
I was actually meaning to ask you to comment with the recent discovery of the connection of fast radio bursts with magnetars, the one found in our galaxy. Can you comment on this a little?
Yeah, absolutely. So I was very excited to see that because since the first repeating fast radio burst was localized in the other galaxy, I think it's been quite a popular model that magnetars are responsible for making FRBs. So Brian Metzger first suggested that it may well be the same superluminous supernova magnetars that make FRBs, because the superluminous supernovae can nicely explain why you would have the persistent radio source in that galaxy. So you could have a very powerful supernova ejecta that's creating the radio nebula, and then the magnetar in the center occasionally emits an FRB. And so inspired by that, I did some calculations on the relative rates of these things. And it turns out that if superluminous supernovae emit FRBs for roughly the same time scale as you expect this nebula to exist, that kind of would match the observed FRB rates. But so at that point, I was pretty happy thinking that maybe superluminous supernovae are the progenitors of FRBs. But I think that picture has kind of become a lot muddier after that. So first of all, the second FRB localized was in a big spiral galaxy, not like where we generally see superluminous supernovae. And then it's still unclear whether they all repeat or only a few. And so discovering the FRB in our own galaxy, it seems to confirm the picture that magnetars emit FRBs, or at least emit some FRBs, but it does not seem to confirm the picture that it's the magnetars left behind by superluminous supernovae. So I think it's probably reasonable to think that some superluminous supernovae magnetars emit FRBs, but that general magnetars can also do it. And so we might expect a weak connection between superluminous supernovae and FRBs, but maybe not the one-to-one correspondence that I'd hoped for.
Okay, thank you. Any more questions from the observatory?
Hi, I have a question.
Go ahead, Kasia.
How many magnetars do we know about? Because last time that I learned about them, I think we knew about one or maybe more.
Yeah, that's not a number that I have off the top of my head, but I think in our galaxy, it's of order maybe like 10 magnetars, something like that.
Okay. And are they located mostly in bulge or?
I'm not sure. Actually, I don't know the answer to that.
Okay, thank you.
There's 10. There's probably a bias to the nearby ones, and so it's probably hard to say.
I would think so, yeah.
Yeah, and the masses of these magnetars, these neutron stars, I could see from your corner plots that you can measure the mass of the neutron star formed. What are these masses? What are the ranges?
So yeah, unfortunately, the mass is really, really badly constrained. So we've treated the mass of the neutron star more as a nuisance parameter. So the luminosity that you get out is kind of the spin period times the mass. It's the angular momentum of the neutron star is the thing that matters. So the neutron star mass has to be included as a free parameter to get a realistic error on the spin period.
Mm-hmm.
But because the neutron star mass does not affect the slope of the light curve, it's not constrained nearly as well as the spin is. So it's more of an uncertainty than a measurement. So we used a prior, I think, just an ignorance prior of the realistic neutron star mass range of about 1.4 to 2.2 solar masses, and the posterior is just basically to get back the prior. So we didn't really make any mass measurements. It's just really to get a more realistic uncertainty on the spin periods, unfortunately.
Okay, makes sense. Okay, I don't see any more questions. So thank you, Matt. It was really nice to have you on such a short notice, and let's keep in touch.
Yeah, my pleasure.
I'll stop the streaming. So thank you, and thank you all for joining.